say, where is my shame when I call your name? So please, don't set me free. I'm as heavy as can be. I will do you harm. I will break my arm. I'm a victim of your charms. I want to be dead. When I'm in bed. I can be so mean. You can beat me. I would like to shame you. I would like to blame you. Just because of my love to you. And love itself is just as innocent as roses in May. I know nothing can drive it away. Though love itself is just as brief as a candle in the wind, and it's greedy just like sin. Alone but sane, I am a love suicide. 'Cause love itself is just as brief as a candle in the wind. It is pure white, just like sin. Alone but sane, I am a love suicide. 'Cause love itself is just as innocent as roses in May. It is pure white, just like sin. Led through the mist by the milk light of moon, all that was lost is revealed. Our long bygone burdens, mere echoes of the spring. But where have we come, and where shall we end? If dreams can't come true, then why not pretend? How a gentle wind beckons through the leaves as autumn colors fall, dancing in a swirl of golden memories, the loveliest lies of all. Hi, it's me on a Saturday. Okay, how's my audio? Okay, you can hear me. It's all good. So, welcome. What's up? How's it going? This is gonna be a bit of an experiment. A bit of an experiment because I'm trying some new things today. I'm gonna try a bunch of new things. But it's gonna be good. You know what? That's what science is all about. Trying new things and seeing how it works. So I have set up a desk cam so you can see me writing things. I'm not sure how like valid this is gonna be, but I did set it up, so we're gonna try to use it. So that's what's up. But anyway, hello. My name is L Little, and I am a physics PhD candidate at the City University of New York. So there you go. There's my accolades. I have a Bachelor of Science degree in astrophysics, and I have like almost a master's degree. It's almost a Master of Science in just general physics. I didn't finish my thesis, but I did everything else. I did most of my thesis. It's not like I didn't even do a thesis. I did most of it. I just didn't present it. So, you know, there's that. But I'm in a PhD now, so who cares? Anyway, so you guys asked for this, and by you guys asked for this meant I offered it, and then you guys said yes 200,000 points times. So we are doing our Twitch community physics lecture, and I have been all over the place about how to do this, what to cover. So boy oh boy, I cut a lot of stuff out I was gonna do. We're not doing any E&M. Sorry, I just didn't make the cut. We're pretty much just doing kinematics and Newton's laws. So there's that. Just apologies ahead of time. I got really excited. I was gonna do fluid dynamics, guys. I was really excited. So yeah, it just means then we'll have to I'll put up a new lecture thing, and then we'll have another lecture and we'll go over other stuff. The lecture, I was shooting for 3 hours. So hopefully it'll be 3 hours or less is the ideal. I don't want to go over 3 hours because honestly, when I teach, I get burnt out around the 3 hour mark. So hopefully it's 3 hours or less, but we'll see. Yeah. And so if you're in the Discord, and I'm going to put up the Discord link really quick. Okay. If you're in the Discord, if you go into the Science Talk section, I have put up some supplementary materials for the lecture, including the notes that I'm going to be lecturing from. I typed these notes up earlier today, so they might be riddled with typos, but the notes are there, so if you can't read my handwriting or if you're like confused by what I'm saying, it should be self-explanatory for the most part and cover everything I expect to cover, hopefully. I also put up the quiz. There was a demand that we have a quiz. So there is a quiz in the Discord. If you can't do it right now, that's fine. Hopefully you should be able to do it by the end of the lecture. So yeah, awkwardly shuffles in the class. A demand for a quiz. I know, like you guys are like, quiz, give me more homework, roast me, grade me. No, I'm just kidding. You guys aren't that crazy. I have to say, I also love how much like role playing we're doing where people are like, sits in the back of class. Like, this is really fun. It's like we're in a real classroom. Yay. Okay. So. There's a few topics we're going to cover. Like I said earlier, we're pretty much going over kinematics and Newton's laws. And yeah, role playing is great. And I love role playing. We should all role play all the time. So we're going over kinematics and Newton's laws, but before I can talk about that comfortably, I want to do a math overview. So we are going to be doing some mathematics in the beginning. And like I said, the math overview is going to be far more detailed in my notes in the Discord if you want to look at those. And if not, it's fine. It should be clear because I'm essentially saying the same thing twice. But if you're a read-along person, I was going to do slides, but I decided not to do slides because I didn't want to make them. Are we going to do any trig? Yes. Next thing so I can copy your notes. Yeah, we're going to be doing trigonometry. Okay, so let's get to our fancy dancy desk cam. So I know it's gonna be kind of hard to see, so I'm gonna write stuff and then kind of like hold it up to the camera, so hopefully that's like a little bit more visible. So that's what's up. Lecture time. Okay, guys. Yay! Physics 1. This is where we're at. So. Let's start with the most important thing. I also wrote Hello World on the paper, so that's a little bit cringe, but I couldn't tell if you could see. So don't look at that. The first thing we're going to be talking about today is vectors. So vectors are, I know. Vectors are a key mathematical tool used in physics. And so how do we define them? How do we define vectors? Vectors have magnitude and direction, right? I'm going to write that down because it's so important. Yeah, magnitude and direction. It's something I learned like 1,000 years ago, and I feel like almost every class I've ever taken since then has taken at least 1 minute to be like, hey guys, vectors have magnitude and direction, remember. It's something we physicists say to one another all the time. As in greeting. No, I'm just kidding. What is scalar and a vector? It's true. Are vectors physical objects? I wouldn't say they're physical objects, but vectors are used to describe like physical phenomenon, like position, acceleration, electric field are described as vectors. So yeah, so vectors have magnitude and direction, as opposed to scalars, where scalars, I'm just gonna write that down too, have only magnitude. All right. Yeah, so scalars have only magnitude and vectors have magnitude and direction. So what does that mean? If I say I was walking 5 meters per second, right? It's a scalar. I'm just going 5 meters per second. It doesn't really tell you which direction I'm headed in. I'm just going 5. If I said 5 meters per second west, that now is a vector because there's a direction associated with it. So a vector is like a dimension above a scalar, and there is something a dimension above a vector, which is called a tensor, and tensors are essentially just collections of vectors. They are represented by matrices, but we're not going to be talking about tensors because they're not really important to what we're saying today. But there is another level, and I think there's a level above tensors as well. So, things multi-dimensional, there's n dimensions in everything, okay? If I say I'm working in 3 dimensions, it's because I could be working in 10, Dimensions are dimensions, and who cares? Who cares? But anyway, back to our handy-dandy little vector, okay? Vectors are described, we write them like this. My vector A, I put a little arrow on top, okay? We're going to use arrows to describe vectors. So, if it has magnitude and direction, here's my arrow. And that means this vector is different from this vector, which is different from this vector, which is different from this vector. So, the angle and the length and the which way it's pointing are all part of how we're describing vectors, all right? So when we draw it in the arrow notation, the magnitude is the length and the direction is the point, right? So these two are roughly the same magnitude, but in the opposite directions. Where this one, I could draw one, and this one is different because it's going off in a completely different direction. So we have it's very spatially specific, okay, if I draw a vector. So my vector A, we can break down into components, all right? So I have some AX plus AY plus AZ. I'm going to be working in 3 dimensions for the beginning of this, but we are going to switch down to 2 dimensions because it's not so important that we work in 3 dimensions, and we may as well just cut one off to make it a little bit simpler. Okay. So I can describe my vector as AX, AY, AZ, and it just means that there are 3 parts of it, right? 3 parts that are different in some very specific way. And so what makes them different? How am I breaking these down, right? I mean, clearly I labeled them X, Y, Z, which might give you an indication that I'm working with axes, right? So we've got, I'm going to draw just a quick little axes right here. So we have X, Y, Z. All right. So if we're working in Cartesian coordinates, and I'm going to be trying to sticking to two-dimensional Cartesian coordinates for as long as possible, but I will reference things in the higher dimensions and other coordinate systems, but we're not there quite yet. So in our XYZ coordinate system, this vector could be described as something like this, right? Just something off to the side where it has some X component, you know, some point where it hits the X, some point where it would hit the Y. This is kind of a shadow, so it's hard to see, but like, and some Z, right? So there's some aspects of it where it hits every coordinate at some point, and we can describe it that way. If a vector has only 2 components, why are you using 3 variables to make vector A? Well, here's the thing. I could say I have a 2-dimensional vector, right? This piece of paper is a plane. It's only 2 dimensions. These vectors I drew here have only 2 dimensions. I can describe them in 3 dimensions because what I can say then is that its Z component, it's like, you know, if my pen is the 3rd axis, here, try to draw it like this. My pen is the 3rd axis, its Z component is 0. So for any extra dimension I want to add, I could just say it has a 0 value for it. If I want to describe it in 5 dimensions, I'd have like 0, 0, 0, 0, 0. So it's up to me. But yeah. This one, I was describing it in 3 dimensions just so I could talk about 3 dimensions really quick, but it could be whatever you want. Yeah, I'm glad these are good questions. Feel free to ask as many questions as you want, guys. It's so important. Especially with how casual and colloquial this is anyway. So like feel free to stop me with questions. But yeah. So we can describe it in components AX, AY, AZ. So these components respond to our axes, right? And our axes, what we use instead or over time is we use unit vectors, which are exactly the same as our X, Y, and Z. I'm just going to draw them smaller. And so now we have a unit vectors, which is their orthogonal basis. Orthogonality meaning perpendicular, meaning everything's at 90 degrees. You swallowed your pencil. Well, see me after class. We'll see what to do about that. And so in the unit vectors, for Cartesian unit vectors, we're going to say this is in the Z hat direction, the X hat direction, and the Y hat direction. And so we just put these little hats on top of our vectors, and a unit vector is just a vector that is completely in the direction of one unit, and it's got a length of 1. All right, so it sounds kind of silly, but these are like the specific ones for this coordinate. We have other unit vectors that we use that are not associated to a unit vector or to a coordinate system, but those are not necessarily important. Like if I say in the n hat direction, it just means in the normal direction, which means it's perpendicular. This is if you're talking about a lot of specific type of geometries. We'll say something like, like if you have a flux through a shape, you have something flowing through some 3-dimensional curve, right? It's gonna flow out in the the normal direction. It's going straight through it, but that direction can be described with a bunch of other things. So we'll just say n hat. It's like the generic version. Y hats. I mean, I'm not sure why it's a hat. It's like, that's just the notation we use. It's a little hat. I think it's because it's supposed to be like a vector symbol, but like it's not the full vector because it's a unit vector, so it gets a little special hat. But yeah, interesting question. Okay, so back to my regular vector. I'm just gonna write it again. My vector A, I'm gonna write it yet again like this. AX, X hat, plus AY, Y hat, plus AZ, Z hat. All right, so this is like a more accurate component form of my vector A. where ax is just some value, some scalar number, in fact, of the x component. So it could be any number. I mean, it could even be like e to the I phi or something. It doesn't have to be anything. It's not really limited to anything. It could be negative, it could be positive, it could be 0, it could be some funky imaginary thing. It could be whatever it wants to be, really. But ax is a number and x hat is the direction. So we have our vector with our direction. All right, to my notes. Okay. So, yes, I'm gonna write out an example really quick. So here I have a vector. Here, let me draw a little page break. Okay. So here's my vector, and we're gonna call it, so cleverly, call it A, because why would I rename it? My vector A. And we want to know how long this is, like just more information about it, because it's not useful to us if we don't know anything about it, right? So what we do, because we are working in the lovely, lovely Cartesian coordinates, which is just a fun system to work in most of the time, for vectors anyway. We've got, I made these like little shadows, right? Little drop downs, right? So now what does that look like? A super duper fun right angle. And we freaking love right triangles, team! Because why? Because right angles, triangles are so like, we know so much about it. If we know about the right angles, if we know about right angle triangle, we're like, It's like having something that's a circle. It's just one of those things we know so much about that we're like, that's perfect. I'm good. I don't need to worry about anything anymore. My life is complete, and we understand. Okay. So this section is going to be AX, and this is AY. Right? Yeah. Absolutely. So we have our AX, AY. And so, like we said, this is what AXAY is. But if we want to know what this total magnitude is, the hypotenuse of our angle, if you will, we can just use our good old right triangle. Yeah, so we know the Pythagorean theorem, which is a squared plus b squared equals c squared, right? And in this case, if we translate this to our coordinates, right, we have ax squared plus ay squared is equal to just a. I'm writing this as absolute value of a vector, which is how we write the magnitude. If you see a letter like this, just for hee hee ha ha's notation notes, it's huge. Okay, magnitude is written as either absolute value of a vector or just a. Like if I were to say, like, if you're reading a bunch of stuff and it said a vector, a vector, a vector, and then just start saying a, that means it's just the magnitude, not necessarily the direction. It's not the vector. It's just how long is it. Yeah, it has a little house. So, squared. There's a square there. All right, so what we can do is we just, here's the solution of this. To get the magnitude, it would just be ax squared plus ay squared. That's fine. That's the same. So you just take the square root of the components. And if this were in 3-dimensional, just to be super clear, if this was in 3D, you would just add another third dimension. You just add it on. It's exactly the same. Nothing crazy happening in 3D. It's pretty straightforward. But that's how we'd find the magnitude. All right. And so similarly, we can also find the angle at which this vector is from some axes. In this case, it's axis x, by using our lovely, lovely SOHCAHTOA, right? I'm just going to write it down. Right. And if we remember, SOHCAHTOA is sine theta equals opposite over hypotenuse. Ka is the cosine. theta is equal to adjacent over hypotenuse. And TOA is our tangent, lowercase t, tan, theta is equal to the opposite over the adjacent, right? Am I using capital A? Yeah, I did see the reel that you sent about Queen Elizabeth and Drake talking about SOHCAHTOA, and I was like, how do I incorporate this into what I was doing? It was so good. It's very funny. It's a really good Instagram reel. It's just Drake and the Queen Elizabeth talking about this. It's so funny. But yeah, so if we know all the lengths, we can find the angle, or if we know the angle, we can find the lengths. Both are good. They're all variable. You know, they're all good. We only need to know a few things to find other things. And that's really the key to physics, I feel like, is just knowing enough to get by. All right, cool. So we got our vectors. I think we know what we're talking about. So, more vector stuff. Let's talk about vector algebra. Because now we have a vector, but like, what are we going to do with it? Am I right? So, hearing that again felt good to my brain. Oh, it's good, it's good. Okay. So vector algebra, right? How does that even work? I'll tell you right now. So, vector algebra. We've got a few things here. There's a few key things. So I'm going to talk about addition, subtraction, dot product, and cross product, which are like, essentially we have adding, subtracting, which is kind of the same thing, and two types of multiplication. There are other things we can do with vectors, but they're not going to be super relevant. I don't want to go over like 100% vector math, but it's just something to get our feet in the water, and it's great. I haven't thought about dot product and cross product in so long. I was literally explaining cross product to my friends over the past week and discussing faster tricks on how to do cross products and stuff. So it's like super relevant to me. It's in the zeitgeist. I'm like, bruh, thinking about it. So theoretically, we have vector A, our good best friend here, which we're going to switch to 2 dimensions just to make it a little bit easier. We have ax x hat plus ay y hat. And now we have another vector. We'll call vector b. All right. We're going to call it b. bx x hat plus by hat. All right. These are our 2 vectors. They're just generic vectors. They could be anything. I'm still speaking very theoretically, very vaguely, okay? So, we want to add and subtract, which is all good and hood. So, basically, what our goal is to do A plus B equals something. Who knows? Who knows what it is? So, the reason I broke it down in a component form, as you may be able to suppose, to guess ahead of time, is that we can only add and subtract like things with like things, which is pretty much a very common thing in algebra in general. If you recall, things like, here's just a quick side note. I'm going to write this, and I hope this isn't too confusing. But if I had like 3x plus 5y plus 2x minus 3y equals z. We don't care what it equals, right? This is just an algebra note. To simplify this, I could, manipulate it some ways, right? I have this 3x and this 2x. 3x plus 2x is really 5x. And I have 5y minus 3y, which I could say is equal to positive 2y. But you're just combining like terms, but I can't combine the x's and the y's like all into one thing because I don't know what x and y is and they're separate. So we can do this. It's the same thing with components, right? Because even then we have x's and y's. We're still doing x's and y's. It's the same idea, so it's pretty straightforward. So the sum and simultaneously this, so the way I think about sums versus subtractions is a little bit different. They're the same in my mind. All I think of if I'm subtracting something is I'm adding a negative. So I think they're exactly the same, but I know that's like kind of a weird mindset to come from. But essentially, I think if you know how to add, you know how to subtract. You just add a negative version, right? So there's that. So we have a vector plus b vector is going to equal ax plus bx in the x hat direction plus ay plus by in the y hat direction. So, and again, ax, bx, ay, by are just some numbers that we can find that are there, right? So we just have this relatively simple thing inside. And the key ingredient to know about vector algebra is that you get a vector at the end, or about vector addition. You add two vectors, you get another vector. I get essentially a third vector, which I can call vector C, or some resultant vector. So let's do a quick example. I'm gonna write, what happened? My pen bled through. Okay. I'm gonna use the back of the paper because I don't want to waste it. But let's do some examples because it's important. Okay. So I'm gonna describe A as 3x minus 2y plus, or no, we'll just keep it in 2 dimensions. 2 dimensions. I could do that. I'm sorry, I'm so used to 3-dimensional. And we'll call this like 5x plus 1y, and I'll create a C, and we'll do, let's see, 10 minus 15. Okay, so really quick, here's the class participation time, all right? You guys, I'm gonna give you we're gonna work for 5 minutes, okay? I'm gonna write some things here. We're gonna do A plus B, B minus C, and then A plus C. Okay, so I'm gonna give you guys 5 minutes. So you might want to take a screenshot or something of this so you could use it to reference, but I'll try to hold it up as long as I can. And just try to do the vector math. Give me, what is this resultant vector in terms of x and y's? You can leave it in component form. That's totally cool. I don't need it in magnitude. That's fine. Right, I know. It's hard to keep things down to 2 dimensions sometimes, to go back to the basics. But okay, I'm gonna leave that somewhat visible, and I'm gonna put my timer on. So this is exactly how I teach, guys. So I kind of apologize, but not really. So okay, here's my 5-minute timer. Go ahead and do math. I'm gonna sit here quietly. But if you have questions, just let me know. I'm gonna do it too, but on a paper that you can't see. You're basic algebra girly. Does an orthogon have an octagon? An octagon has 8, but it looks like you wrote orthogon like orthogonal. Accountants just use basic algebra. Okay, so we've got money math. Vector calculus. You're making a joke about orthogonality. I got you. orthogonality. All right, B minus C is... All right, cool. Just a gamer that stumbled into physics class. I mean, aren't we all? I know, it's kind of funny about thinking about doing a physics class on Twitch. I'm just like wondering how many people are gonna click on this and be like, oh, you were literal? That's like actually what you meant? Okay. Also, my like let's do some science mug. I did it especially for the stream, guys. It was like middle school math. Math is crazy. Like how people are like defining math. Like when you take a math class and they're like, this is this. And you're like, what are you actually teaching me? Like, what is going on here? You know? I took a class called differential equations and linear algebra when I probably should have taken a differential equations class and a linear algebra class, but I took them combined, which I think was easier for me. But if I took them separately, I would have had the math minor. So that's the bummer, but that's okay. It's okay. I don't know. I don't like math classes, so I'm glad I didn't have to. But at the same time, I would have had a math minor and I would have looked really smart. Okay. We have another minute and a half for anyone who is still doing the problems. No pressure. There's still time. Yeah, well, I can't get a math minor. Well, actually, I wonder if I went back and took that class and then just like was like, hey, can I reapply for graduation? I might be able to, but I don't care. I don't care enough. I was like in my undergrad. I probably should. I probably could. I just don't know if I care enough to go back. Oh. Oof. Right. I mean, I have a minor degree in Japanese, and I'm like, minor degrees don't really matter. They're kind of like just things you get. I mean, I've never personally run into someone who's like, oh, I have a minor degree in this, and that's what I'm like working in. I'm like, usually you do your major degree is what the big one is. Oh, I would look smart, like, as opposed to, I don't know. I feel like getting a math degree is like a different level of like, whoa, crazy. Physics degree is like, whatever. Basic bitch stuff. Only on factoring, bruh. That's how I felt. I went to a summer school for astrostatistics, and I'm not a statistics or math person, and I have to say these people like knew so much statistical math. I was like, what's going on? Okay. So that was our 5 minutes. So guys, I hope anyone with a math degree in business. Yeah, that's like before we get to the example problem, there's the Simons Foundation is like huge here in New York. Almost everyone I know has some association with the Simons Foundation. They fund a lot of grad students. The guy, like Simon of the Simons Foundation, apparently he's like a math physics guy, right? But he made a fucking algorithm that can predict the stock market very, very well, and that's how he made all his money. And I'm like, what? You can just do that? And now he's like super bajillion $1 million rich, and all he did was make like a dumb thing, and like it's just really accurate. And I kind of hate this guy a little bit because he has a lot of money and I don't, so that's basically why I hate him. So basically I'm mad because I'm poor, but anyway. And I'm glad you're vibing with the honey lemon. Yeah, I know. I want to use my math powers to get rich. That's like all I want. Okay. But anyway, back to the example problem, guys. What did you guys get for A vector plus V vector? B vector. I'm sorry. Because I got a number, but I don't know what you guys got. What did you guys for the X and the Y? I'm an interactive lecture person. Yep, that's what I got too. I also got 8x hat minus 1 y hat. Yeah, we've got confirmation. Hell yeah. Okay, for the next one, b vector minus c vector. What's up, team? We got -5 plus 16. Does anyone have a second answer on that? The signs are wrong and your second value is a little messed up, but you're close. You're very close. You're very close. So yes. So what I got, wait. Okay, I'm gonna write my answer. Now we can check because I could have done it wrong, guys. Do not take my word for anything. So I got -5 x hat minus 14 y hat. So I think that's right, but we'll look at it. So b minus c for the x direction is 5 minus 10, which is -5. And for then we got 1 minus minus -15. You're right. I got it messed up. All right. Because it's minus, right? 1 minus -15 is plus 16. You're good. You're good. No. You're good. This is why algebra is the most dangerous math you'll ever do, guys. It's so easy to make mistakes. I make mistakes all the time. So we're good. Yeah, 1 minus -15 is plus 15. All right. Good. We're jamming, guys. Okay. So for the next one, a vector plus c vector. I messed it up too. (13x minus 17y) is also what I got. All right, cool. We're in good standing, guys. Good job. Okay, so that was... I can only think of Soul Eater. What? Okay, so vector addition, subtraction, pretty straightforward. You just break it down into components and you're good to go. And again, if you had 3-dimensional vectors, you would just have an extra z and you just focus on it like it's all, just put it in a column, add it up. It's good. Okay. So, dot product time. Yeehaw. The dot product. So, again, we have our vectors A, and we have our vector B. And now we have a big old dot in the middle. It looks like multiplication. Is this where the multiplication sign comes from? I think it is. But who cares? So A dot B. What kind of values do we get from this? We, in fact, get a scalar value, and it is no longer going to be a vector. So that's something to keep in mind. So here we go. I'm gonna write it out in component form, what A dot B is, just so we're clear. It's basically AX, BX, the sum. It's the multiplication of the components, and then you sum all of the components, is the idea. But I'll write that out because some people don't like hearing math, including me, so. AY, BY plus AZ, BZ. So you just do like the x's multiplied summed with the y's multiplied, and I wrote it in 3 dimensions again. That's me being a little pedantic. When do we use this? It loses its sense of direction. It does lose its sense of direction. So dot product comes up for different types of formula. So what was, I had an example of one, which I don't think we're gonna get to, but work. One of the ways to find work with force is work is force dotted into position, or like the radial position is how work is defined. So you would dot it because work is a function of is energy, and energy is a scalar, and so you need to get rid of that like value. If it loses the direction, we use the absolute value. So usually we can use it. It's that it's a little bit funky. I'm like hesitant to say use the absolute value, only because, like, for example, if I was doing like a work calculation, usually all the values are positive. So there's not many situations where you can get a negative situation. But yeah, I guess you could use the absolute value because the direction you would assign to a scalar number, like a plus or a minus, usually is based off of your specific situation, right? So if I have like a negative 10 joules, I lost 10 joules of energy. It usually means because something else gained 10 joules, and it's only because I'm considering myself the like system, I'm losing it, but it's not like disappearing because energy can't be created or destroyed. So it's a little bit wonky, but you could. But the general idea is that you just multiply the components, add them up, and then you get the scalar it's just a number, really. It's just a number. My hand gesturing keeps getting in front of the camera, so I apologize. But that's the dot product, and dot product comes up a lot, especially in the Maxwell equations, which I was gonna get to, but there's no way I'm gonna get to Maxwell equations today. I was supposed to be done with all the math by this point, and I'm not even close to being done with the math, but that's okay. We're jamming through. We're vibing. I'm gonna jump straight into cross product. Yeah, this is a math day. What else are you guys doing on a Saturday afternoon if not going over math? Okay, so the cross product is back to our lovely A and B, except now I have this little cross in the middle. Wow, that's pretty handy. So what does a cross product... Cross product is a lot more difficult to explain and to find. And cleaning your closet? Hell yeah. I actually need to do like laundry and stuff, but you know, whatever. I'll just do math. Who cares? So the cross product. We have a vector A, we have a vector B, right? And what do I get from my cross product is I get another vector, a third vector that is now perpendicular to my two vectors. The plane that is created by these two, I can get a third one that is completely perpendicular to it via the cross product. That's the general idea. And you might be like, why? Literally what? Who cares? There's a lot of reasons for it, including things like torque and stuff. Like torque acts in a perpendicular to the two different things and stuff like that. So it comes up in some cases, but it's a little wonky. Do you still right hand rule if you're left-handed? Yes, you have to use your right hand or it doesn't work. If you want to use your left hand, you just have to take the inverse of everything, which I never remember to do, so I always just do it wrong. Torgle. Torgle to Torkle. So, A cross B can be found by using a matrix determinant. I assure you this is the easiest way to explain and find a cross product, even though it's going to seem a little insane. So if you don't know how to find the determinant of a matrix, boy oh boy are we going to tell you how to do it right here. So first of all, it's the determinant of a 3x3 matrix. Don't get too scared. So we're going to say x hat, y hat, z hat, And then I'm going to say AX, AY, AZ, BX, BY, BZ. Whoop. So the determinant of this matrix right here. I was always right. Right hand rule. Yeah, so the right hand rule is like how you can think about cross products too, because you have your like this shape is like your two perpendicular lines, and then this one's perpendicular to those. So you have this 3 space that we're working in, which is our like right hand rule. So that's kind of the idea. If we're talking about the right hand rule, I feel like I should explain it, or people are gonna be like, okay, crazies. But yeah, so that's like kind of how to think about an orthogonal basis of unit vectors, right? Or any vectors, really. But, so the determinant is such a thing. So we're gonna start with, this is gonna be really silly. Okay, you have the x hat, right? Because that's the first one right here. And then when you cover this first x hat like line, and then you take this like the determinant, this tiny little 4x4 array, or 2x2, 4x4, holy goly, 2x2 array. So we get AYBZ, I'm going to put it in parentheses, AYBZ minus AZBY, and that's in the x hat direction, minus y hat, because when you do the second one, it's minus, you have a alternating plus minus, but we only have 3, so we don't have to worry about the middle one. And then you cover the middle one, and then you go across and across. So then we get AXBZ minus AZBX. And then we have our z hat direction, so plus z hat. And this one's easier to do in 3 dimensions than it is 2. So if I do it in 2 dimensions, I just put zeros in for the z direction, so I just don't mess it up because it's hard to remember which ones are. So then z, we've got AXBY, AXBY, AYBX. Oops. Punch my microphone. And this is the new vector that describes our cross product. Wowee, golly gee. Is this how noise canceling headphones work with sound waves? Kind of. Almost. It's like, yeah, because noise canceling headphones can like take a frequency and find the inverse and just play the inverse of it. So not quite, because this is taking like, it would be like something adjacent to it. It wouldn't be quite the inverse, but it's an interesting idea. I'm trying to think about sound waves, but yeah, so this is the cross product, and cross products again are super relevant for certain types of terms. They come up a lot in electromagnetism, and when you have like, there's a lot of like classical mechanics terms that come up with cross product too. Like I mentioned torque. There's another one, I can't think of what it is. Yeah, a lot of B fields though. Electric fields, magnetic fields have a lot of funky perpendicular properties, which is why cross products come up so much. But anyhow, anyway, that is my vector algebra section. How are we feeling, team? How are you guys feeling? I want to try to do a poll just because I've never been able to do one before, so let's try it. How are you feeling so far? Good. Okay. Don't ask. I'll put start poll. Okay. Is there a law of magnetism in space that you account for? Actually, magnetism in space is like a really interesting kind of like it's a really interesting field. Magnetic field. Because like there are a lot of really strong magnetic fields, but at the same time they disperse in a weird way, because what is a magnetic field falls off as a function of 1/r. So they trail off pretty quickly. Not as quick as an electric field, but they're still like important, especially when you have things like plasmas or like you actually laughed. Hell yeah. My jokes are hilarious. I'm a comedian. But no, because was it when you have I took a plasma physics class like a while ago, and so plasmas are all over space in the ISM, in the interstellar medium, right? So it's like you end up getting this phenomenon called magnetohydrodynamics, which is where you have magnetism. Yeah, because ionized plasma, a lot of plasma in space is ionized. A lot of ionized plasma has electrical charges moving. So those electrical charges moving create a current, which creates magnetic fields, and that's where you get magnetohydrodynamics, which is like hydrodynamics in the terms of magnetism. So it does come up a lot. It's kind of funky. Magnetism relative to current also follows the right-hand rule. Yes, it does. Yeah, it's where your thumb goes in the direction of the current and your finger should curl the direction of the magnetic field, is the right-hand rule for magnetism. So if your back B field's this way, you go this way. All right, let's see. Did anyone do the poll? Yes, I got 2 goods. That's 100% of the people who voted said they were good. That's great. That's great. Don't look at the sample size. I figure out how to turn a screw. I mean, it's good. It's like there's something really inherent about this, being able to do this shape with your hands. I feel like that's important. Okay. So, whoa. We talked about all the vector stuff. Okay. It's that, like, it's really funny because, like, what you guys are both describing is, like, when you're talking about, like, angular direction, it's kind of, I have a hard time, like, determining angular direction, like, when it's, like, clockwise versus counterclockwise and which way I want to go. It's, like, a big thing. It's, like, a big deal in, like, how we, like, live our lives. Like, opening bottles or screwing in screws or determining, you know, the angular speed at which something orbits. Angular direction is so important, but it's always, like, kind of a mess. You're like, I don't know. It's harder than, like, you know, left or right. It's funky. It's a funky little thing. Because it's not really left or right. It's like around this way or around that way, right? You know? But I digress. Okay. So now we're going to be talking about derivatives. Derivatives. And again, if you are following along on the notes, this is section 1.3. That's as far as we've gotten. So derivatives. I'm gonna write it down here. dx dy. So this is what a derivative is. You've probably seen it. It doesn't look that crazy. It's really not that insane. What does it mean though? So a derivative is the rate of change that something undergoes in a specific parameter. I'll write this one too. So ddx is like a rate of change in some function of x, which is usually position, right? ddy is simultaneously also position, but in the y direction, where ddt is a time derivative, the rate something is changing in time is the way to think about it, or the rate something is changing in space. These are, I would call these spatial derivatives. Versus my time derivative. And so It's like those are the two kind of keys between derivatives. And so these are so important. It's so important to know how things are changing in time and space, because that's like everything. Like everything we do is pretty much just like, oh, how is it changing in time and space? That's how we observe things in general. Like, you know, if I can see something, if I'm standing next to a tree and the tree looks very, very tall because I'm standing next to it, if I go stand 10 miles away, how tall does that tree look? The height of that tree is dependent, like visually from my perspective as the observer, it's dependent on as a function of distance, because it looks smaller if I'm farther away from it. Simultaneously, like, how does my position change over time? If my position is changing over time, am I moving with some speed? That's the definition of velocity. So that was my funny little hinting at what's to come. But things at a 62-degree angle. I love it. So that's what time derivatives are, and they are determinant on the coordinate system you're using. So again, I'm sticking to Cartesian coordinates. And you might be like, well, t isn't a Cartesian coordinate. T is the secret fourth option of almost every coordinate system. If you work in special relativity at all ever, the fourth dimension that is important is space-time, which is like CT. We call it CT. So you have X, Y, Z, CT. We use 4 vectors because space-time is an important part. And space-time, it's like one word, space-time, like jammed together, created by Einstein, I think. And so space-time is a specific unit. I'm not using like space and time as a general concept, but specifically the term space-time, which is CT, speed of light times time. But we're not getting into that, but that's where T comes from. If you're like, what? You were saying X, Y, Z, and now you're throwing in another one. Yeah. Okay, so I had some examples, but I use better examples, so I don't want to use the examples I wrote down. I don't want to use the examples I wrote down because they're nerdier. I like the tree example. We work in the 4th dimension all the time to understand what's happening. Yeah, like we use 4 dimensions a lot. Like here, the first example, like when I was taking calculus something, was like, okay, here's something in 4 dimensions. You go to ship a box at like some shipping service, right? They're gonna measure the 3 dimensions of the box, how big is it? But then they might also measure the weight, a 4th dimension that is now a factor in how much it's gonna cost to ship the box. You know, like you use these like extra terms to keep these things, to measure things, right? Or, you know, height could be like, yeah, like, so weight, time, sometimes like weird things like pressure. You could do a lot of things with extra dimensional analysis. So it's not like we're not trapped to 3 dimensions. Get that out of your mind right now. 3 dimensions is crazy. Even when we're talking about like physical space, you can get into phase space, where phase space is a factor. It's the imaginary realm of space that is like a factor when you're doing certain things. And it's a little complicated to get into phase space. I didn't want to talk about it like explicitly, but phase space exists, and it's like another dimension to fucking think about. You're like, what? So my quantum teacher said it so well. He's like, nature doesn't have parameters, right? Nature does not have parameters. We use parameters to like try to understand nature, but nature has infinite parameters. And so like, there's no like, we live in 3-dimensional space as being absolutely true, because nature doesn't have 3-dimensional space. That's something we put onto nature, and we are just trying to understand what she's saying. So like, you know, anything's possible. Get over it. That's mean. I'm being harsh. Okay, so the only other thing I want to talk about with derivatives before we get into kinematics is I wanted to mention the del operator. So the del operator is described by this little nambla, and it's got a little vector, right? Because it's a vector. But what is it a vector of? It is literally described as d dx x hat plus d dy y hat plus d dz z hat. And so this little silly little del operator, I'll write it down with words too. Del operator. All right. So the del operator is something that comes up, and it's literally just like a partial spatial derivative of anything. So if you see something like del something, it's just going to give you like how it's completely moving in space. It's pretty cool. It's a cool thing. It comes up a lot, again, in Maxwell's equations for electromagnetism, because like things like electric fields and magnetic fields are incredibly dependent on spatial dimension. And so like we really are interested in how things are changing, how the rates are changing in space. And so you use this, and it's nice because this is for like a 3-dimensional object. So you could have some funky thing, and it's very cool. I actually like this little equation a lot. It's kind of one of those things I see and I go like, oh, I know what that is. Thank God. Oh, it's not scary. So I just wrote it down so you guys wouldn't be scared if you were looking through math, physics stuff, and you saw the del operator, because she ain't hurt nobody. She's just being there. Who is that girl even? Okay, so section 1.4, we are totally on time. 1.4, integrals. Oh, I forgot to write in print. Okay, I wrote in cursive. I usually write in cursive, but like, it's not the most, I should write in print. Okay, so what is an integral, okay? An integral is effectively the opposite operation to a derivative. Yeah? Mark. So it's the opposite of a derivative, but like, what does that mean? Like, what are you saying? Am I right? So, what am I saying? Let's first talk about the lovely situation. Here, I'm gonna pose a situation to you. This is like a real math class right now, guys. I'm like pulling out all my math stuff. Okay, I have a curve that looks like this. All right, I made a little plot of a little curve. Wowie, cool. But now I want to know how much space is under the curve. What is the area under that curve? I don't know. How do I find that out? Who could say? Who could say, right? So this curve is some f of x, right? Just some function. So what I could do to try to guess, right, is I could be like, let me put a big rectangle underneath it, all right? There's my approximation, big rectangle. It's not that accurate because clearly it's speaking out over here and it didn't get all the way up to the top. So here, I raise you this. Smaller rectangles. It's gonna be so accurate. How many rectangles am I gonna draw? It's like 1, 2, 3, 4, 5. All right, 5 rectangles. It looks a lot more accurate to the curve, right? But you know, we're still like sticking out a little bit in some places and also not quite making it in other places. So here, I raise you. What if I did like infinite rectangles? Like an infinity amount of rectangles. Like just so many. It'd be like so perfect, right? That's basically what the idea of an integral is. Like an integral is taking this thing and doing a bunch of like super infinitely small little rectangles underneath to essentially get the area under the curve. And so that's like an easy way to imagine. It's something I have to come back to when I'm thinking about integration and really being like, what am I doing? What am I thinking about? The integral is essentially finding an area under a curve. You have some function, you just want to know what the area underneath it. What does that mean physically? Totally depends on what you're integrating, why you're integrating it, but like, that's the basic concept. And it's sometimes nice to come back to these base concepts and keep them in your mind when you're doing something more complicated, because the base part's never untrue, right? The base part is just like the basic, like, you know, the foundation, and then you get all the way up to the top and you're like, I'm fucking disoriented and dizzy, I'm gonna fall over. But then you're like, oh, the foundation's still there. Like, so that's what I like to think. It's just the area under the curve. casually walks through a calculus lesson. I mean, I had to like think. I mean, it took me like, I don't know, 2 hours to type up these notes in LaTeX about how to do this math. So it took me a second. It took me a hot second. I had a review, but it's okay. Infinite knolls in a trench coat. For real, you have infinity knolls down under this curve. How many knolls? So this is a Riemann sum. What this is, so there's, I don't remember the equation, and I didn't write it down, which I probably should have. But you know, you get your like sigma something, 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 something. I don't remember. But basically, to find the area, if you do it through the rectangle way, is that you would sum up the area. Like, I know the area of this one rectangle. You just add all the rectangles together, and then that's how you get the area, right? And so it's fairly accurate for some things, but yeah, if we want to go infinitesimally small, we end up going to this swoop symbol like this. This is my integral symbol, and I'm gonna write f of x dx. All right, and again, this integrand, the integrand is what's inside of an integral, if we're talking vocabulary. So we have our integral f of x dx, and f of x is just this function that we had, the original curve, and we want to know how it's changing dx, right? We want to know that in this direction. I could do dy if I was interested in this one, but we're worried about this dx. So there's so many things to say. There's so many things to do here. If you look at the notes that I have on the Discord about this, I do have some better like visualizations of Riemann sums and a little bit more explanation of like the concept of the infinite sum. So I'm skimming over it a little bit. But anyway, it's mostly what I said. It's just not like I wrote it out on paper and it looks nicer. Yeah. And so basically you get this thing and it's just a bunch of sums, and you can sum it between some limits of integration from like a to b. Like if this was, you know, our a was 0 and our b is this, we can know what it is in this specific region, or we can know what it is over like all space. You can have an integral from negative infinity to positive infinity, and that can be valid. It depends on whether it diverges or converges, which is a whole other topic of conversation, but like, you know, it just is what it is. And if there's no limits of integration on it, it is called I always forget the word. Ooh, I wrote it down. Indefinite integral. I know what it is. Okay, sorry guys. But yeah, it's called an indefinite integral. And indefinite integrals are far more dependent on whether they converge or diverge, either at 0 or infinity usually. But some of them converge, and it's like, you know, no matter what like region you're looking over, it's just going to be something, or if it diverges, then the region is actually super important. So, but again, and this comes from, derivatives come from like limits and limit notation, or integrals come from Riemann sums. So that's kind of where they come from if you wanted to like take it back to more base principles, but I don't like doing base principles, so we're not talking about it. Try to remember the start of f of t for your favorite kinematic equation. Yeah, it's all good. Okay, so my last math point of the day before we get into hardcore physics. It's not gonna be that hardcore. Don't worry. Is I want to talk about coordinate systems, because I brought up coordinate systems before. I've been talking about them the whole time. I wrote it in cursive again, but it's too late. One of my teachers only writes in cursive, and his tests are all handwritten, and like his homeworks are handwritten, and it's kind of crazy. I'm like, damn, that's crazy. So there's 3 main coordinate systems that are used. But realistically, you can make your own coordinate system. Like there's no one's like forcing you to use them. It's just there are 3 that are really easy to use. So why not use what's there? You know, if it ain't broke, don't fix it. Don't reinvent the wheel. You know, all those little phrases people say about things. So the one, I'm going to do it in 2 dimensions, just to make it easy for us. For the first 2, because the other one has to be in 3 dimensions. So we have x and we have y. These are our xy coordinates, right? So this is our Cartesian system. All right, and our Cartesian coordinates are x, y, z. This is like, I think it's like the first one you learn about when you start learning about coordinates. It's also associated with like map making, which is kind of like where its history is. Like, you know, if you look at maps and you see like latitude, longitude lines and stuff, those are kind of because they're Cartesian. Because Cartesian is related to what is it? What is the word when you do map making? I had it in my head earlier. I almost wrote it down just because I knew I'd forget it. Cartography. Yeah, so I think it's like the similar, like word wise, but Cartesian coordinates, and my freaking camera came out of focus. But yeah, so that's the idea, and it's straightforward. So I'm not gonna go too deep into that, but it'll be important when we talk about. Oh, sorry. The other thing is that we have unit vectors for every coordinate system. So ours is gonna be x, y, z, but sometimes people also use I, j, and k. They're exactly the same, but you know, it depends on what you want to do. Oh, I didn't put a hat on z hat. So I, j, k, x, y, z are the same. My teacher likes to mix them up and I hate it, but I wish he just picked one. That's okay. And so for our second one, in 2 dimensions, we have polar coordinates, all right? IJK feels better. Yeah. It's you know, it's just a preference thing. I feel like I switch between XYZ and IJK a lot, and I don't know. Like, I just have to pick one for the day. Autocorrect loves to mess with people. Okay. So, if we're doing polar coordinates, we are now thinking more about circles and circular things. So if you look at like ships use it a lot, like radar maps. It's like a weirdly specific thing. But if you, it's like more like you have you're more worried about like something at the center, the origin, right? And you point some function, some vector r. Your r vector is now the important one. It's some length away. It shows how far away something is, and you want to know what angle it's at. So it's mostly for working in circular type of things, and I'm going to try to draw like a circle. Pretend that's a perfect circle, but that's okay. And so, you know, I can draw an r in any of the circular directions, and essentially I just need to know how long r is and what angle it's at, and that points me to a specific point on a circle. So, you know, and the circle can be, you know, really big, it can be really small, and so it's I'm glad it looks like a perfect circle. We'll take that. And so this is a fun coordinate system, I think, especially for things like circular. If you're doing, I used to do a lot of if you do angular kinematics, which I didn't want to bring up because that's a lot. But angular kinematics problems are things like you have an ant walking on the hand of a clock, right? So just by it standing there, it's moving like this, but it's walking towards you. So now it's making a spiral. So that's the trajectory we want to follow. How do we describe the spiral as a function of time? It's easier to use polar coordinates than it is to use cylindrical coordinates, or it's easier to use polar coordinates than it is to use Cartesian coordinates, because now we're talking about something moving on a circle. Basically, the radius is like decreasing over time, the angle is changing over time, and that's like a situation where we'd be more like, oh, I just want to think about it in circle forms instead of trying to break it down into x, y coordinates, because that's really difficult. Like, you can do it in x, y coordinates, it's just like a lot harder. Yeah, and so it's just one of those things that's like, it's easier to just do it this way. And so now our unit vectors, all right, polar coordinates. Our unit vectors are now r hat and theta hat. They have to be great at modeling AC power. You know, for sure. There's something, circles are just one of those like shapes and like geometries that is just primo. There's a lot of things that function very well in circular geometry. As much as like people, I had this, so I'm sorry, a little bit of a side note. When I was teaching coding to these like high schoolers for a little bit, and it was really funny because they were like, I was like teaching them just like basic coding stuff, so I was doing a lot of math, and they were like, oh, like, well, we don't need to know any of this like circular geometry stuff. And I was like trying to explain like how circular geometry is used in like physics and stuff, and they were just like blown away and also upset because they're like, oh god, I hate circles. And I'm like, no, you'll get to a point where you love circles. Circles are actually really nice. And they're like, no, you're lying. And I was like trying to convince these teenage girls that circles are cool. But I get it. I was a high schooler once. I remember hating geometry and circular stuff. I remember being confused. In fact, I'm still confused. So, you know, at the end of the day, who's telling who what? All right. But we've got R hat and theta hat. Every time I think about AC power, I get mad at Edison for killing elephants. So he uses less efficient DC power. Yeah, no, dude, there's so many weird science stories about two people being like pissed off at each other and then doing something absolutely insane and being like, anyway, I'm right. And you're like, what the fuck are you doing? Like, why? Calm down. Yeah, no, the AC DC power issue is very silly in hindsight and very like, get over yourself. What the fuck? Oh my god. Okay, so back to polar coordinates. So now our R vector, our R hat is in the like, our unit vector R hat is in whatever direction our radius is in. And our theta hat is actually a perpendicular to it. What was my pen dying? All right. Theta hat. So we have theta hat's now this thing that's like perpendicular coming off of our R hat. And that's what it is. So that's pretty cool, pretty convenient. Except if this was my R vector, now my R hat is like over here. And my theta hat's over here. Right? Now it's over here. And remember earlier when I was talking about vectors and I said that like the direction was really important? So the lengths are the same. They're unit vectors. So they're all of length 1. But now they're like completely in different directions because theta is going to change as R changes and they're not like a stable basis necessarily. So that kind of sucks. Which is why polar coordinates are frequently translated into Cartesian coordinates, because Cartesian coordinates don't change with position. Cartesian, you could pretty much translate every type of coordinate system back into Cartesian coordinates because Cartesian coordinates don't change, and that's like one of the key things about them, even though they're not the best to work in. If you're worried about something, and this is, again, it really comes down to like, what's the geometry of the problem? What are we worried about? What are we looking at? Because if I'm just like, if I'm a ship at the center of the origin of this, and I just need to know where something is, I'm totally fine. But if I'm like, oh, I need to go send something out somewhere, and I need to know which way to have a guy start walking, like, you might want to break it down into sines and cosines. Basically, we go into sines and cosines to make it into Cartesian coordinates. And if you look at the notes that I put on Discord, I have, under the polar cylindrical coordinates in section 1.5, I have a figure that I stole from Khan Academy. There you go. I tell you who I stole it from, but I have a figure that I stole, and then I also put the translation into Cartesian coordinates for you in case you were like, how is that related? But basically, R hat can be cosine theta x hat plus sine theta y hat, and theta hat is negative sine theta x hat cosine theta y hat. Don't feel like you need to memorize that. Just look it up every time. Oh my god, no one memorizes it. That's lame. But polar coordinates in 3 dimensions are called cylindrical coordinates because our x and y plane is a circle. So if we take that circle and I'm able to move it up and down and make it like long circle, that's just a cylinder, right? So cylindrical coordinates is the 3-dimensional alternative to polar coordinates, and it's just, you just add a z at the end, and that z is exactly the same as the z from Cartesian coordinates. So that's nice. That's really easy. Good to remember. And so that's that. Those are our coordinate systems. Let's see. What was I going to say? Okay, so then our third coordinate system, which I'm not going to draw because it'd get really complicated, but it's roughly the same idea. If theta hat is like a function of r hat, right? And it changes. It's always like going off the tip. That key is going to be in the next one where we talk about spherical coordinates, which is pretty much only in 3-dimensionals. There's no 2-dimensional sphere because that's a circle, which then we use polar coordinates. So spherical coordinates are only in 3D. And in spherical coordinates, it describes something in a spherical geometry, as you can imagine, but we basically have almost the same unit vectors. Let me write it down. Spherical chords are now r hat, theta hat, with the additional mysterious phi hat. And phi hat is just another angle. So if we have, here's my circle, right? And we have r and some r at a function of theta, right? We see theta. And then we have another axis because r can be like this way too, right? It could be like womp, womp, womp. And that's our theta, or phi. That's our phi hat. And that's a little bit hard to visualize. I probably should have put it in my notes, but I didn't put it in my notes. There's a lot of really good like visuals people have made about like how to think about the phi hat direction, because it just makes it's just another angle. Because you know, we have r and we can move it this way and we can move it this way. And basically it's like phi is this way and theta is this way, and r could be anywhere on the circle. As far out or close in as it wants to be. And so we have our 3 coordinate systems, which are like our base systems. There's a lot of other coordinate systems that are not important to talk about unless you're talking about something specifically. One of the ones that comes to mind for me is there is a cosmological coordinate system that happens when you are like talking about things like positions of things in the universe as a function of inflation. So there's like a lot extra stuff in there, but you can tell, like we can calculate it. It's not like impossible, but it's just a different coordinate system. And coordinate systems are importante. So did I use this other side of the paper? No, I have a clean side of the paper. Cool. I'm gonna take a 5-minute break because I just said a lot of stuff and I've been talking for an hour and a half. So that was like an hour longer than I planned to spend on this. But that's okay. That's okay. This is why I gave myself 3 hours. Okay. But I'm gonna take a 5-minute break. And just like, we're just not gonna talk about math for a second. I'll be open to questions. If anyone has questions, this is the time for questions. But I'm just gonna take a little bit of break so we can like, you know, reset our brains. I've got my timer going, so there we go. That was all the math. That was all the math that we were going over. Easy peasy, right guys? But no. My disclaimer is like, if any of this math is like confusing to you or you're like upset by it at all, I totally understand. For one, I totally fucking get it. Like, math is so weird and confusing and hard to conceptualize for some people, and I'm definitely one of the people that math is hard to conceptualize. And so, you see the quiz? Yeah. And so I have a hard time with that type of stuff, and so I get like, I don't expect people to like jump in and see this for the first time and completely understand it. It's mostly here to just like introduce these ideas to you, or maybe review them if you've seen them before, because I think they're good to know. I think it's like good to have this type of like, I don't know, math know-how. And so that's why I wanted to share it with everybody. But yeah, no pressure, no stress. But also, you know, now you have access to these notes that I wrote up, in case they come up later and you're like, oh, I remember her saying something about that. What was it? Reference materials are the best thing you can get out of any class, and you can't change my mind. Like, I feel like you'll learn, the most important thing you'll learn is how to find a reference material to something you could figure out later. Like, that's just how it be. Oh, yeah, my notes are definitely skimpier on the second half because I had planned My original plan for the lesson, as I look back at it, was so I just wrote I'll just show you really quick. This was all things I thought I could cover, which was a little bold of me. I don't know why I thought that, but I was gonna go over kinematics, Newton's laws, work energy, electricity, and magnetism. But that's like, I don't know why I thought I could do. So I cut it down because I figured I may as well just go over a few things well than try to go over everything in a terrible way. But yeah, it's gonna be good. It's exciting. I think it's gonna be fun. I like kinematics. I really like kinematics. I started teaching. The first class I ever taught was like a kinematics-based physics class, and it was really fun. Well, it was fun for me. My students hated it, but like I had a good time. And at the end of the day, that's all I remember. Num 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 num. And that's all that matters. Yeah. Yeah, I used to teach almost the exact same thing I taught you guys, but in like 3 hours sessions. So pretty much this is like what I would do in a typical like tutoring session, is I would just be like, okay guys, let's go over the math, because they never knew what the math was. Which is fair. It's hard to remember all the math, you know, when you're not looking at it. When you're not thinking about it all the time every day. Who's thinking about math every day, am I right? It's not me. It's not me, I swear. All right-o. I know, my quiz questions are fucking hilarious. I love them. And I like totally like made them up really quickly, so if they're hard to like if they're hard to do, that's my bad. I did not test them at all. You a smart person? No way. No way. Oh no, I did it. You did the quiz? I'm gonna pull up the quiz really quick. Nice. I'm glad you did it. It's not that crazy. It's a pretty straightforward quiz, I think. Where is it? Where is it in my notes? Lecture quiz. There it is. Yeah, it's only 4 questions, and there's only like 2 real questions. But it's good. I think it's good. I think it's like, I try to ask questions based off of like what I want you to take away from the lecture, so I think it's effective. Right? Yeah, it's pretty straightforward. But also, Mage Hand, because why not? It's very D&D related. I just like wish teachers had more fun with like questions that are like this, you know? I wish there was more like, it just makes it more fun. I don't know. Why not? Also, when me and my friends, like, not the group I play D&D with right now, but like my other group, a lot of us are like STEM people, and we get really into the weeds sometimes about like what is physically possible in the D&D like universe, and we get really into like, well, hold on, how much, you know, if Mage Hand can only carry up to 10 pounds and you're trying to do all this, like, is that possible? We have actually drawn out free body diagrams before. We have done a lot of math and stuff, so it feels like accurate to the D&D experience, in my experience. So I think that's fun to share as well. But we're back on the clock, kiddos. It's freaking time to learn. So what are we talking about? We're talking about kinematics. All right. Kinematics. Can we see that? Can we read that? Okay. So, whoa. Let's talk about our kinematic parameters. Do I teach classes on here? This is the first time I've ever taught on Twitch, and it's partially because we've got what's it called? I made them do a community challenge, and you guys wanted a physics lecture, so here's the first one. Mage Hand can hold a sword. Whoa, that's crazy. I like don't know how heavy a sword is though, but like I wanted this really bad. Yeah, I hope you guys are getting what you wanted because this is insane. But anyway, let's talk about some stuff. We've got okay, good. I'm glad you guys are at least getting what you wanted because I'm like, really, this is for you more than it is for me. So like, hope you guys are like, yeah, this is so fun. So we're gonna be talking. I'll write them all out actually, just to save some time. Displacement. And all right, there we go. So displacement, velocity, and acceleration are our three superstars here in the kinematics universe, okay? So displacement, what is it? Displacement is like, essentially, it's a vector. Notice I put x hat. It's a vector that is describing like your total change in position. For example, if we're thinking in 1D, here's like a line, right? And I'm gonna say this is 0, just a number line, okay? Like, you can move like this far, and then you can go back like this way, and then you can go like this. And all I'm worried about is like where you started and where you ended, okay? So your displacement in this case would be 0 because you started exactly where you ended. I wish I had another color on me. I have black. This is like not the right pen, but that's okay. So if I went to another one and I went like this, and then I went back a little bit, and now my starting position's here, or no, my ending position's here, my starting position's here, like your total net displacement is this vector, right? From this like start to end. So that's what displacement is. So it's like position, but it kind of accounts for you going back and forth and stuff like that without it being a whole deal. Like it's not like how far you walked, but how far did you end up is the way to think about it. This is also a time where I'm gonna introduce this concept that what does the negative sign mean? Because it's gonna be important for us. So I'm gonna draw another number line. That's not a straight line at all. Oh my god, my desk is like curved right there. Oof. Okay. We'll pretend that's a straight line. So I have a line and I have some 0, right? I'm gonna call this direction positive. I'll put it plus in a circle, and I'm gonna call this direction negative, okay? So if I move positive 5, it's gonna be 5 in this direction, right? Simultaneously, if I move negative 5, it just means I'm moving in this direction. So negative just means the opposite of positive, and that's going to be the way we really want to conceptualize it, right? Is that if I'm going, and this is true for displacement, velocity, and acceleration. If I use a negative acceleration or negative velocity versus positive velocity, I just mean like I'm either going forward 5 feet or I'm going backwards 5 feet. It doesn't necessarily mean like one is slower or one is different. It's just like the opposite direction, okay? And it sounds like I'm stressing something that's going to be like inconsequential, but it is kind of an important and weird way to think about it. So especially with velocity. So velocity is if displacement is essentially our position vector, right? Velocity is it's speed with direction, okay? It's not speed, because speed doesn't have direction. I could say I'm going 50 miles an hour, and I'm going 50 miles an hour. It doesn't tell you which direction I'm going in. If I said 50 miles an hour west, then that's a vector. So, there you go. That's back to our vectors having magnitude and direction. The 50 is the magnitude. We need a direction for it to be velocity. The absolute what's it called? Absolute value. I'm like, it's the bars. Absolute value of the velocity is the speed. So they are related to each other, but one's like a little bit less complete than the other. But if I said I was moving, so I have an object and it goes 5 meters per second. And then at some point in the future, it starts to go negative 10 meters per second. It just means that it is switched direction and is now going at a faster speed than it was before. Right? So the direction of these terms is mostly just telling you, like, think of it going forward or backward. People like to say left or right too. It doesn't really matter. Just as long as you have some kind of opposite opposing directions, you could say up and down. If we were doing an underwater thing, I could say I'm going up or down. But like, it doesn't matter. Acceleration is quite the same, where I can be accelerating in this direction or I could be accelerating in this direction. Doesn't really matter. We like to say accelerating in the up and down direction if you're thinking about being on Earth, because gravity we feel and experience an acceleration due to gravity based off of the gravitational pull of the planet that we live on. And that gravity pulls us down towards the center of the Earth. And so we tend to call it negative, like a negative acceleration. Negative 9.8 to be specific. But like basically we're just like, if it's acceleration due to gravity, which we call little g because it's our homie, little g's negative. Little g's going down in the ground. But general acceleration can be up or down. I could also throw something down where it will accelerate even faster because I put extra oomph on it. But that's not it doesn't necessarily, so the negative sign is just a direction. Just keep that in mind. All right, so we know what our things are. We know about displacement and velocity and acceleration. So I'm gonna write our sweet, 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 delicious kinematic equations, right? I didn't put vectors on them, so keep that in mind. They pretty much are, but I'm going to write a series of equations and just bear with me for 1 second. All right. Cool. So here are our handy dandy kinematic equations. And kinematic equations are, if I were to memorize anything from physics, I would like to memorize at least this first kinematic equation. It's super useful because like what this first one tells you, I mean, we'll go over all of them really quick, but like this is something that it could be like you could actually use in your day-to-day, not your day-to-day, but like maybe if you were stranded on an island kind of day-to-day, you could use this and really like be able to tell like distances of things. There's an example I wanted to use for this lecture, but I like ran out of time and was lazy. But I will describe it to you in words, the less exciting version. There's a film called As Above, So Below. It's a horror movie. I love it. And it's about these lovely, crazy people who decide to go spelunking in the French catacombs. And then they go down to hell. And it's crazy. But while they're descending into craziness, there's a part where they realize they're trapped. And they find like a well. And they get a rock. And they drop a rock down the well. And they just like listen to see if it hits the bottom, right? And I'm just like, you know what you could do there? You could tell exactly, you could pretty much guesstimate pretty close to how deep that thing is if you count how many seconds. You get your time, right? Because this is just a function of time, right? Your delta x is all you want to find. Your v naught is 0 because you're dropping it. You don't care about that term. Acceleration due to gravity, roughly 10. So if you just take that t, however many seconds you count, t squared, square it, multiply it times 10, divide by 2, you can kind of guess how far it's going to be. Not perfectly, but enough if you're like, I'm going to jump down there. You might as well know. And then if you were like, oh, I have this much rope, you can kind of figure out. But anyway, before I start getting into the specifics of it, let's talk about these equations, right? So, when I have this delta x, I realize I didn't explain what the capital delta x. So capital delta refers to a change in variable. So I could put capital delta T is another one, like capital T for temperature. And it just means the final minus the initial, right? I'll just write that down really quick. Delta equals final minus initial. All right, cool. So we have delta x, our change in displacement, right, is equal to v sub 0, v naught, t, which is our initial velocity, times time, plus 1 over 2, a acceleration, t squared, times time squared. So that's what that means. And from there, you can kind of understand what the rest of them are, where vf is our final velocity. So this is an equation for the final velocity squared as a function of, you know, like position and acceleration and things. The final velocity is a function of time, and position is a function of velocity without acceleration. So these are all helpful. These are all kind of like, you can kind of derive one from another. And if you were in a traditional physics class, as a teacher, I would probably do this for you on the board, but I don't want to because I know it's gonna go over a lot of time. So like, but but yeah, this is like the general conditions, and it's pretty straightforward. Yeah. So here is the dealio. Let's do a quick example that I'm going to make up. I mean, I thought about it earlier. I just didn't write it down. So I'm flying by the seat of my pants. Imagine, if you will, you're standing here and you carry the One Ring. You have carried the One Ring all the way from Rivendell, and you are now standing on the precipice of Mount Doom. Okay? Cast it into the fire, says your friend Samwise. And while you're debating as to whether to cast the One Ring into the fire, we want to know, you know, how far down is it gonna fall? What's delta x? All right, what's delta x is our question, right? What's the displacement of the One Ring as it is cast into the fires of Mount Doom? Okay, here's the fires of Mount Doom. And we want to know this. Beep, beep. Delta x. All right, so that's us. We're Frodo Baggins here. Yeah, and so what do we know? So this is how I would start a problem, is we know that we're dropping it from 0, right? We're just gonna like, we're currently holding the One Ring like over the fire, and we're like, do I let go or not? That's where we're at, okay? So V naught is 0 meters per second, right? Units are super important, and I realize I didn't go over units when I was talking about that, but that's okay. I'm gonna force them down your throat now. So our initial velocity is 0 meters per second, right? Our acceleration is just acceleration due to gravity because we're just dropping it, right? We're not throwing it, we're just like letting our hand go. You play the unit game. Units are so nice for trying to figure out what's going on or whether you made an answer that makes sense. So our acceleration due to gravity is negative 9.8 meters per second squared. Yeah, I definitely use unit analysis like too much to be like, is that right? And so our acceleration is 9.8 squared. Do we know our final velocity? No, we don't know what that is. Do we know our initial position, x naught? We're going to call our initial position 0, okay? Because we can. I can say I'm starting from 0. That's totally fine. And I can say that the negative direction is positive, or the downward direction where it's falling is positive, because that's totally fine. Again, I am the master of my own universe, and I can create any direction to be whatever I want. Yeah, so like, I'm gonna be very clear and say this is the positive y direction. I'm just gonna call this y because it's down. I could call it x if I wanted to, but actually, to be clear, just to be really clear, I'm going to call this delta y the whole time. Just to be a little more correct. So yeah, so we know v naught a, we don't know v of f, but we do know x naught, and we don't know what, like, what's the other one? xf is like what we want. I'll just put a little star there. But that's like what our goal is, okay? So I like to write down everything I know about the problem and then go to my equation sheet and just be like, here we go. What do we got? What am I looking for? What do I need? Right? Yeah, we do have our acceleration. And so this first one is the one we want. But let's just rule the other ones out, because assume we like don't know anything. We're like super concerned because, again, our friend we're on the edge of Mount Doom and we don't know what we're thinking about. Okay. Is this like out of focus? I'm so sorry. There we go. So we can't use this one because we don't know delta x. We don't know v of f. So that's a little frustrating. All right. For this one, we could find the final velocity knowing the acceleration, but it doesn't have anything related to the displacement, which is what we want to know. So we could find it, but it's not useful to us. This one, all right, delta x, that's what we want, but we don't have this final velocity, and so that's going to be a little tricky. The general rule of thumb is that you should have an equal amount of equations to how many unknowns you're looking for. So like in this example, I'm only technically looking for one unknown, so I should be able to use one equation. Were I looking for two, if I wanted to find final velocity and displacement, then I would need two equations. And so on and so forth. If you have 5 unknowns, you'll need 5 equations. And so it's pretty straightforward. So we're only looking for one, right? And so let's go to this first one, and I'm just going to write it out like this. So here, just write it. Delta y equals v naught t plus 1 over 2. And I'm going to put g in here because it's a gravitational acceleration. T squared. All right. I'm just copying it down from there, just straightforward. And so then we have, I'm going to write y final minus y initial, right, equals v naught t plus 1 over 2 g t squared. And so let's plug in everything that's 0. That's my favorite number because it makes things nicer. So v naught is 0, right? Shoop. That's 0. Y naught is 0. I just did 9.8, but it could be 9.81. I like to keep it to 1 sig fig. We could round it to 10, but I'll stick with 9.8. All right, so we have this. So now, if we take out all our zeros, we have y final equals 1 over 2 g t squared. And in this thing, I'm going to assume we know time. Because we can count that. That's something that's like, it's like a value that we can find as, you know, we drop it, we cast it into the fire, it's falling, we count it. Let's say it takes 20 seconds, all right? I didn't write that down earlier. Again, I'm flying by the seat of my pants here. I'm improving physics to you guys, so try my best. So time is 20 seconds, okay? So y final, to see how far down, I mean, I imagine it's really long. That seems how it be. I feel like my headcanon of Mount Doom is that it's a 20-second drop. It seems really long. But maybe we're very small. Who could say? So y final we can find by just putting 1 over 2. Because I called this direction positive, my gravity is also positive. So keep that in mind. So it's a positive 9.8. And that's just because I defined that earlier. Meters per second squared. My 8 is funky, sorry. And then we have 20 seconds squared, time squared. And so then Mount Doom is, where's my calculator? Oh, I hid it somewhere. Okay. Some amount of math later. 9.8 times 20 squared. Divide by 2. 1960. I don't know what you got. I got 1,960 meters. That's an insane height, but you know, that's Mount Doom, baby. Yeah. So yeah, so we got 9,600, or not 9,000, I can't read numbers. 1,960 meters. Is this a fun time to tell you guys I think I have a learning disability? I'm pretty sure I have a learning disability, but I haven't been tested, and you can't test a lot of adults for certain types of learning disabilities, so I might never be able to tell, but I'm pretty sure I have dyscalculia, which means I read numbers wrong. But amongst other things. So if I write a number down and then read it out loud and it's totally wrong, I think it's mostly because I have a learning disability. You know, there's just some things where you're like, oh, maybe I have that actually. I think I might try to get tested, but you know, who can say? But anyway, but that's how you find something like that. And that's how our kinematic equations work. They're pretty straightforward. Like, just for funsies, we can also go find V final, because now we have everything else. So let's just do this one, this equation right here, where we have V final equals V initial plus AT. Let's just do it. So VF equals V naught plus AT. So again, V naught is 0. A is gravity and T, so VF is 9.8 times 20, because I decided it was 20 seconds. And that is some number that I should know. 196. Is it 1960? Wait. 9.8 times 20. I think it's 196 meters per second. But yeah, it's pretty straightforward. And so, like, the way to think about this stuff too is like, no, it's all good. I'm like, you're off by a factor of 10, bro, but that's fine. That's, in my mind, that's like a reasonable number to be off. Oh, alright, BF. Alright, so, like, the way to think about all this stuff too is we can get really into unit analysis. So, like, for this one, I need paper. I need more paper. Ooh. So, units. So, we have position, we have our X. What do we measure distance in? In SI units, of course. We're gonna use meters. You could use kilometers. You could use centimeters. You could use millimeters. They're all meters, right? So I always do, like, a meter is M, a kilometer is like 10 to the 3 M, a centimeter is 10 to the negative 3 M, or 10 to 2, sorry, centimeters. And this is 10 to the negative 3 M, alright? Yeah. So that's like our unit for position. And again, it depends on what you could use. If you want to get fancy, you guys see, what is this called? Now I can't think of what that's called. It's 10 to the negative 10, but, I can't think of his name. Angstroms. You got it. Thank you. I'm like, oh. I've got the curse of when you're teaching someone something and you forget all your words and you're like, uh-oh, I'm dumb. All right, velocity, similarly. So what is velocity? Let's define it again. It's distance over time. The dude from Futurama. So velocity is distance over time. And we measure distance in meters over seconds in base units, right? Which is where like meters per second comes from. It's literally just you have distance, you divide it by time. Distance over time is just meters per second. Of course, I could have any distance on top and any increment of time on the bottom. I could have angstroms per hour if I was going to be a dick. I don't know why I would do that, but I could because no one's telling me not to. I am the master of my own universe. And at the end of the day, that's all you is. The master of your own universe. All right, acceleration. Okay, so what is acceleration? It is velocity over time, which is in fact distance over time, right? If velocity is distance over time, then acceleration is distance over time, which is where we get meters per second, which is meters per second squared. That's where that comes from. The power company using kilowatt hours. Oh, yeah, that's a funky one. I always get confused by it. I'm always like, wait, a kilowatt hour? Huh? Like, I have to think about it. But yeah, so meters per second squared. And so that's where our units come from. And just because I'm talking about, we had meters and we had meters per time, and then we had meters per time, right? So what is that? What does that mean? I'll take this. This page can be gone from me. Well, I need this still. I knew I need it. Okay. Do you want your electric bill in coulombs? I don't know, maybe. That'd be wild. I feel like it'd be crazy. It's just like weird to have any number. A special new unit called billions. That's a dumb unit name. Okay, so I'm gonna write this out again. All right. So x is equal to v naught t delta x plus 1 over 2 a t squared. Right? That's what we said before. We all agreed on that. And what can I do with this? What if I did this? What if I said d dt of x? I wanted to take the derivative of this equation. I know I did not describe how to do derivatives earlier, but I described what they mean. So the derivative of this is a function of t, right? Because this is x of t. I'm going to write the independent variable in this equation is time. So the ddt of x of t is now v naught plus at. All right, v naught plus at. If I go back, so another way to write ddt, yeah. So ddt of x of t is equal to just velocity of t. That's how I'm defining velocity, is that it's the ddt of x of t. And I just said ddt of x of t is v of t, which is equal to v naught plus a t, right? Which is one of our kinematic equations. It's one of the ones I wrote earlier. It's this one, v final is equal to v initial plus at. We just derived it. We just went bam, there it is. That's how we define velocity. So what we can then do is we can take another derivative in time, right? I'm going to write it like this. d squared dt squared x of t is equal to d dt of v of t. And this d squared dt of squared, it just means I'm doing two derivatives. It's just how you write it. So if I take two derivatives of x, it's essentially taking one derivative of v, and which is just d dt of v naught plus a t, right? This function, which is, if I do the derivative, a. It's just a. And so, as we imagine, the d dt of v of t is how we are now defining a of t. And I'm saying this all really crazily, but like, so of a as a function of t is equal to the derivative in t of v of t, which is equal to the second derivative, dd squared, of x of t, which is just acceleration a. Yeah, I'm glad this is what you were thinking about. And that's where like derivatives are important, because the rate of change of position in time is how we're defining velocity. The rate of change of velocity in time is how we define acceleration. And you could keep going. There is the time derivative of acceleration is then called jerk, and then the time derivative of jerk is called snap, and subsequently crackle and pop. But nobody uses those. Those are bullshit, but they exist. So have fun with that knowledge. Yeah, I think jerk is used by engineers on a certain level, but I do not know why you care about the acceleration changing, but it's just not for me. Who knows? Everything's possible. Again, we're all the masters of our own universe. So this is how you describe a. Similarly, I described earlier that derivatives, the opposite of a derivative is an integral. If I had a function a of t, you could go backwards. I could go from this a and get some new, go back all the way back up to this equation. Like, it's totally possible to go backwards and forwards. That's the beauty of math. That's like how it is. So it's kind of crazy. So I'm going to draw this really quick just to further cement how we are going to visualize and think about these three things, because it's super important. Super important. Super cool. Actually, I want to draw them on top of each other. My desk is not good for, it's not like the most flat surface, I'm realizing. I usually like have like a bunch of papers on top of each other. So I'm like, all right, so this is going to be x of t. This is going to be velocity of t. And this is going to be acceleration of t. All right, so I have some plots, right? So if we go back to this equation, I'm actually going to underline the most important ones here. So that's important. That's important, and this is important. Okay. So, this equation here for position is a function of t, right? And we have a t squared. So what is a squared plot look like, right? I'm asking you genuinely. It's not a facetious question. If I have some function, I make a plot and it's something t squared or x squared, what does that look like? What is the name of that shape? I'm gonna wait. Because I believe you guys know. There it is. It's a parabola. And so we have a positive parabola here. It's a square. So we have a parabola, right? So this is kind of how our position will change. This is what our trajectory will look like, actually, right? Over time, it'll, start to move and it'll get really big really fast. Which is why when we did the cast the ring into the fire problem, the distance got really big really quickly because I had it running for so long, for 20 seconds, right? That's really long. But it's because of this, like, parabolas get really big really quick after a certain point. So back to our lovely integral. What did I say an integral was, guys? The area under the curve, huh? So I'm just gonna write this as like, this is x squared, right? This is some x squared kind of value. I guess it's t squared. We'll put t. Just to be clear. So, what's the area under the curve, right? It's like, or not quite, but it's like, I'm doing it backwards. Sorry. But that's something to keep at when we go the other way. But we have an area under the curve. That would be going this way. But, so we have this next one. Our velocity equation is a function of just t, right? It's just v naught at. So, been a TA for 6 years. I know, right? They're like, I don't know, 2. And you're like, what? What are you saying to me? So if I have something that's just a function of t, and this is like a weirder question, what does the plot look like if it's just a function of t? If this was a parabola. And it's not a square. I'm gonna draw it, guys. It's a line. It's not a flat line, but it's a line, right? So there's our v of t, right? I'm gonna draw area under the curve. So there we go. So if this is what our position looks like, this is what our velocity looks like, because this is just a function of t versus t squared. And then it's the slope of these lines, right? That's what this is. The slope of the line is the thing. So what's the slope of this line if we're going backwards, right? The slope of this line is pretty flat, pretty straightforward, So, and also it's just a function of a. This is just a constant, right? A of t is a, is what I wrote. There's no t. T is nothing. So we're just gonna have it's just a line. It's just like a flat constant is what our thing is. So if we had this and we were to do it graphically, you would take the area under this curve is this. Area under this curve is this. That's how that works. But you see how it gets smaller, right? We kind of expect that to happen. So that's kind of the relationship between displacement, velocity, and acceleration. And so, yeah. Is there anything else I wanted to say about that? Check my other note. I have like 2 sets of notes that I'm lecturing from. No, that's pretty much it. Okay. Get that. Did I do the other side? Okay. No, we didn't. I have another side. So, Newton's laws. Are we ready to move on? Are we feeling good? Are we feeling strong? You guys feel so physically strong after doing all this math, right? That's what makes me feel like I go fucking fight a bear. Just kidding. I can't fight a bear. What did I say? Newton's laws. When do we learn quantum gravity? Never. Don't talk to me about quantum gravity. Yeah, I have cat ears on. Ah! No. They're really subtle, which is why it's fun to wear. Yeah. No, I know. You know how when you go straight from kinematics, and then you're like, okay, quantum gravity. Straightforward. Exactly the same. No steps in between. Alrighty. So, whoa. Newtonian mechanics is fun. Wow. Do you hear my enthusiasm? No, I'm just kidding. I actually don't mind Newtonian dynamics and stuff, but just it's like one of those things I remember learning like Newton's laws and being like, this is crazy. And I think some of it still sits with me. I'm like still kind of like, oh, I remember all those free body diagrams. I remember all those frictional forces. You want to learn more about quantum? I also want to learn more about quantum. I wish I was better at it. I should try teaching quantum to see if I remember anything about it. I'm not a quantum guy. I just like don't get it. I'm kind of dumb. I'm quan dumb. Quant dumb is what I am. Anyway, no. I mean, I have to take a qual in like a few months, so I should learn more about quantum. Really. So Newton's laws. Newton's laws. There's 3 of them. I'm gonna read through the 3 just straightforward, so we're just like on the same page. Okay. The first law is that an object at rest stays at rest, and an object in motion stays in motion at constant speed in a straight line unless acted on by an unbalanced force. All right. It's pretty straightforward. It's just that things kind of want to be doing what they're doing. It's inertia, right? Like if something's moving, it's going to want to keep moving unless something's going to stop it from moving. And if it's sitting still, it just wants to keep sitting still. Like, you know, that's just the first law of motion. The second law is F equals ma, or that force is related to acceleration, which is like the big one, right? The big one. And then the third law is that forces exerted between objects are equal and opposite. So, again, Newton's laws, like, while, like, you know, kind of from a physics science standpoint are profound, you know, especially for, you know, no one having written down before, kind of, I kind of hate how, like, in media, they're used metaphorically all the time. Like, I get it, but also, like, I feel like people use, like, the equal and opposite language, or an object in motion stays in motion, as, like, a metaphor in, like, books and TV and stuff, and I'm always like, is that all you know about that? Like, give me someone you like Pythagorean theorem as a metaphor for life. That would be fucking sick. I want to see it. So sometimes I'm like, ugh, it's a little pretentious because, like, from a literary media, it's kind of overused, in my opinion. There are other laws you can use, guys. There are other laws you can use to be, like, hippy dippy. Oh my god. Side note, my E&M lab that I was teaching, we had them do at the end of every lab, we had them answer these questions that was like, oh, like, you know, you based on the principles we like learned today in class, like how would you use this in real life, or like where do you think this would exist, to try to like have them relate it to something they knew. And I had a lot of students come in and be like, whoa, man, like positive charges are like positive people and negative charges are like negative people. And I'm like, whoa, no, like literally, like what is electricity used for? Not like on a metaphorical scale, guys. Sorry. But like I would get so many answers like that, and I'd have to read them and be like, electricity can be used in wires and for your house. Like, it was really funny. But, like, I guess I get it, but it was also funny. I'm like, don't take it in like, very literally. I'm asking you literally how electrons are used. Like, yeah, when writers write smart people but don't know how. Oh my god. Okay. Another side note. If I can figure out how to do this, like, without getting in trouble, I would love to do, like, a reaction video or stream to the movie Escape Room. Because I rewatched it recently, but the thing is that, okay, the main character of Escape Room, the horror film, is like a physics college student girl, and I'm like, what? But it makes me, I get like so, there's like a lot of like subtle rage I have about how she's written, and I'm like, it'd be really funny for me to just like go off on it, but I need to figure out how to do that, because I'm like, can you do reactions on stream? Can you do that on Twitch? I don't know. I know you can do it on YouTube, but like I don't know if you can do it on Twitch. But if I can, you guys, we're gonna fucking watch that movie. It's gonna be hilarious. Logic gates in a circuit and logic in philosophy. You know they are. Whoa. Whoa. Blew my mind for a second there. Anyhow. Anyhow, Newton's laws, we've described them. Okay, so here we go. F equals ma, right? Back to the note taking. So if F equals ma, from a units perspective, what are the units of force? So we have, what are the units of mass, right? It's a kilogram in a good old SI units. And acceleration, as we described, was meters per second squared. So now if force is kilograms times meters per second squared, what do you think the units are? I'm going to write it like this. Kilograms meters per second squared. The units are, of course, a kilogram meter per second squared. It's really straightforward. Yes, and then we call a kilogram meter per second squared, we call a Newton. Capital N Newton. I'm going to put units. Newton's 0th law. That's true! There's a 0 law for thermo. That's so funny. Asimov. Right? Who else has law? Kepler has laws. I think Kepler also has 3 laws. I wonder if he has a 0. The secret 4th law, right? The fig ones. The good old fig Newtons. But yeah, so the Newton force unit is a kilogram meter per second squared, and it literally just comes from multiplying a meter per second squared acceleration to a kilogram. So pretty straightforward. Yeah, I feel like the 0 law, Newton's 0th law, is gonna be something that like compensates for like dark matter, right? They're like, oh, actually, because of this, dark matter doesn't exist. It's actually part of the 0th law. Oh my god, that would be the case. Especially because people are like, Newtonian dynamics doesn't work on a large scale, like. Right? Oh my god. So. Yeah, so Newton's laws. So let's draw a free body diagram. Okay? Because I was talking about forces, and I was talking about balance and stuff, and so we need to figure out what the hell that means. So here's a box. Here's a box of undeterminate whatever. What is it? Who is it? We don't care. We have a box sitting on a surface. Cool. Sounds good. What forces are acting on it? Well, we have gravity because it's just sitting on this planet, am I right? So I'm just gonna draw that, right? Gravity. I mean, technically I should put a little hat, like a vector sign on it, right? So we have acceleration to gravity. We have gravitational force, right? But if I have one force on it, then it's moving, because this is an unbalanced force equation. So why is it not falling down? Will you be arrested if you violate Newton's laws? In fact, you will. The time police will come and they'll throw you in jail on Jupiter. You get to go to the big red spot. That's where they send all the Newton's laws criminals. So it's sitting on some surface, and that surface is exerting a force equal and opposite to the force being pushed out. This is where the equal and opposite comes from. And we're going to call this normal force. Isn't that from an old cartoon? Who could say? And so normal force is the normal we're using in this context is the normal that means orthogonal, which means perpendicular, which means it's just coming out the opposite. So normal force is normal to the surface. Keep that in mind. And then once we have that, bada bing, bada boom, that's a perfectly balanced free body diagram. I'm going to write that down too. Free body diagram. All right. So we got a free body diagram. It's sitting there. Just living its life, right? What was that first law? What did it say? An object at rest stays in rest. Well, it's resting. Look, so cute, sitting on the shelf. What a baby. So I'm gonna draw another thing. Uh-oh. He's on an incline now. And here's my box. Okay. So that's my incline. That's some function theta, or some angle theta, right? Oh no! Why could we, what? Anyway, what forces do we have acting on this right now? We have gravity, right? Because gravity still exists. So gravity's here, but how does gravity acts only in like the downward direction, right? Okay, that's a little funky, right? Here's G. Label my gravity. Here's my gravitational force. And we have a normal force because I said if it's not flowing through a table, the table must be pushing back on it, right? Yep. And so, uh-oh. But normal force is normal to this surface. So now gravity and normal force are like funky weird to each other. That's a bummer. Or is it? But also, they're not balanced anymore. What's going on here? We've got something else. There must be something else if it's just sitting there, right? So I'm gonna draw it like this. Like a little fly buzzing around. Okay. So we have, if I straighten it out, so normal force is normal, chilling up here. Then we have gravity off at some angle. Uh-oh. Does this look like I'm maybe breaking something down into like components? Okay. So back to the vector talk, guys. Vectors are everywhere all the time. So this is G. But it's off by some angle. Theta. It's the same angle, theta. And so that doesn't help us, but what we can do, and I'm going to describe it in a thick black pen. Oh my god, punch. I have too many things like right in my face, so. Is we have this is some G, and we have also right? If we break it down into like components, that's how it looks. And so what is this? If G is our total vector, right, then we have some G in the Y, G in the X. So we have back to our SOHCAHTOA, back to our, we know an angle, we know the magnitude, and so this one is the adjacent side, so it's cosine. So this is G cosine theta, and this one is going to be G sine theta, right? So now we're almost balanced, right? We have our normal force is balanced with this G cosine theta. Pretty good, pretty straightforward. But now we have this other part of G that's kind of making it look like it's gonna fall down. Uh-oh, we're not balanced yet. That sucks. So there must be another force. There must be another force in the way. And what I'm gonna tell you right now is there's a force we're gonna call lowercase f, and it is a frictional force. If anything, we'll call it Fs for static friction. And Fs is going to be in this direction. It's going to balance. So vector math is going to come up forever all time, so just get used to it. That's one thing. But the other thing is that we have all these balances. So when we do free body diagrams, most of the time the goal is my pen is like fucking me up right now. It's not working. Sum of forces is 0. That's our goal. with free body diagrams. And so for this example, if we sum all of our forces, this is equal to like G plus N, of course, equals 0, right? Because I said it's equal to 0. G is negative 2N. It's exactly equal and opposite. So N equals, I'll put a negative sign to remind me that that's negative. G. And so I could then find the normal force if I wanted to. I could find the gravitational force because these are all forces. So each one of these, due to the second law, is equal to MA. MA, right? And this box has some mass, M, that we know. We just know what it is, right? We can just measure it and know. And so typically we would just, that's kind of how you would go about like solving a free body diagram. This one is not interesting. It's not a very interesting problem. So it's why it's kind of like straightforward. It's just a box sitting there, but it gives you an idea of like a really basic kind of example before we get into something more complicated, like this one over here where we have this really fun shape, right? We've got angles, we got thetas, we have friction, you know, we're like jamming, vibing. So let's sum them up. Here's my sum of F, right? We've got, I'm gonna write negative G sine theta, right? I'll just call it, I'm calling this side negative, I don't know, it doesn't really matter. Minus G cosine theta plus normal plus friction. Yeah, because the sum is just add them all up. Plus a minus is a minus, right? I was saying they're the same. And we know this is equal to 0. So if we say 0 equals the same, G sine theta minus G cosine theta. Ooh, COS. This pen is not ideal. Plus N plus FS. Then we get this, right? I'm going to write it in a way that's a little bit easier for me. FS equals G sine theta plus G cosine theta. And knowing all of these forces, you can always put F equals MA. You can always say F equals MA. We can plug that in for any one of these, and we can solve things like, what is the acceleration? It's 0. These are balanced forces. The acceleration is 0. But you could solve for normal force. You could solve for the frictional force. These are values that we can solve for. I think in a typical class, you would solve for things like, you know, what is the frictional force? What the frictional force has a little bit weird because there's a coefficient of friction, right? Mu. That's in there. Is it mu? What is it? What's the frictional force equation? Me not Googling it right now. There's a mu in there. I just don't, it's just mu n. There you go. It's a function of mu n, right? So I'm just going to write that here for us. Where n is the normal force, right? So these are related to one another because if you have more normal force, your friction will be affected. If you had less normal force, your friction will also be affected. Also, I put this sub S in there because there's static friction and then there's kinetic friction. It's when there's like, if you have friction of something that's sitting still or friction of something that's moving, there's like a barrier you have to overcome, which is where you get 2 frictional forces, 2 frictional like variables. It's a function of muon. Bruh. Tis indeed. I love, mu is one of my favorite Greek letters. You know how you get like, I don't know, I'm assuming everyone gets partial to at least one Greek letter. Mu and lambda are the ones I like, amongst others. I mean, what else? I don't know. Those are probably my favorites. I guess I like eta too. I like mu. lambda, eta, all the good ones. But yeah, so that's what a free body diagram is. This is how you find something. Oh, omega's good too. I like capital delta. If I were to pull up my quiz. So again, if you guys are new or you just showed up, I'm gonna put the Discord info back in the thing. I didn't type it right. Don't look at me. I only know math. I don't know how to type, guys. Those are two different skills. If you want to join in, if you're in the Discord and you go into the Science Talk section, or if you want to join the Discord and go to the Science Talk section, you can check out the notes that I've been lecturing from this whole time. And you can look at the quiz that I wrote for this session, because by popular demand there was people wanted a quiz, and so I gave you guys one. It's pretty straightforward. You've both downloaded. Nice. And so going over the quiz, can I like do this really quick? Hold on, let me see if I can do some sneaky stuff on the fly. Window capture. It's me like trying to be a cool guy streamer. I'll do display capture, sure. Okay, hold on. Boop a doop doo. Doo 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 doo. And then I'll put it like that. And then move it. Oops, not that one. And then move it. Okay. There we go. That kind of makes sense. So here's the lecture quiz that I made up for you guys. So there's only 4 questions. They're pretty straightforward. Also, it's not like a real quiz. This isn't school. Like, I'm not gonna grade you. I will release answers to the quiz and also put them in the Discord, just in case someone wants to like check their work and like see if they're doing things right. But I didn't want to do it beforehand because I literally wrote this like 30 minutes before I was supposed to stream. So like, I'm running all over the place. I'm being crazy. But yeah. We want the units of different types of variables, because it's super important to just have recall of some of these units in SI units. So keep that in mind. Some of these are vectors, some of these are not. So I'm going to have you pick out which one's vectors. It's pretty much a true or false type of question. And then here's a vector math. These are just like tip to tail adding, subtracting vectors. Like the DM forgot they were going to DM that day. That was pretty much how I was. I was like, okay, I'm just jamming, dude. We're just going for it. But yeah, our vector math question, which is about you going on a grand quest. And you need to know what the party's total displacement was, because that's cool. And then we have a force question, which is mostly related to what I just did, where, let's see, what's the question? You're in a dungeon, your party's wizard wants to use Mage Hand to get help to get an item off of a high shelf. Mage Hand can only exert force up to 44.5 newtons before being dispelled. The item in question is a box holding a prized gem with a mass of 12 kilograms. Assume the box mass is negligible. So I want you to draw a free body diagram about the box in the hand. And then, you know, can your wizard successfully cast Mage Hand? It is a super hefty gem. I wanted it to be like something kind of crazy, but I figured like you're in a dungeon, so like you must be looking for something crazy, right? Why would you be there? If not a 12 kilogram gem that's maybe magic, I would assume. Yeah, dude, that's worth you know, spelunking in a dungeon for. You can like buy a kingdom with it. Hope Diamond, my ass. 12 kilogram gem. That's what's up. And so that was the vector. So those are the questions. Those are pretty straightforward. Yeah. And then these were the notes that I wrote about math. It's mostly math overview. If that thing existed, people would commit war crimes to own it. They would, dude. It'd be insane. I would love to see, like, what the biggest diamond or gemstone would be, right? Like, I'm sure there is one in a museum somewhere or something where they're like, oh, it's probably insane, but like 12 kilograms is like dense. That's big. But yeah, so I have all these here. This is all in the Discord again. And it's just pretty much me covering what I went over before with some, like, I have some nicer visualizations that I stole off the internet. So it's not like my shitty drawings, and yeah. And they do end pretty abruptly, and it is mostly because I ran out of time and also realized that I would probably, just going over what I had, I'd probably be pretty close to 3 hours, which seems accurate because I'm right at about 2 hours and 40 minutes-ish of streaming. So, yeah, I'm pretty much, I think the timing went really well. And I was able to, like, I wasn't, like, trying to, like, jam through the whole time. I was also, like, telling fun stories, so it was good. I think that worked out. So that's pretty much all the information I have for you right now. And again, each of these is a rabbit hole. We could get into more complicated kinematics. We could get into more complicated Newton's laws, free body diagram situations, but 20 minutes isn't enough time. That would be stressful for you and me, probably, because I'd be like, do you guys get it? And you guys would be like, oh my god, stop talking to me. I want to go to sleep. So that's what's up. But that's it for me. This, we found the ability wheel in Mass Effect 1. It's one of those things that I'm like, I'm glad there's like a little clip of it, so I'll never be able to forget how insane that was to me. But yeah, so that was our first potentially of multiple physics lecture from the community challenges. So thank you for showing up. Thanks for being a part of it. Thank you for everyone who submitted 200,000 points. That was an insane amount of points. It was too many points, so I will probably not put that many up in the future. Well, like, for something like this, I think 80,000 is like a high number that will still take time to achieve, but not like months and months and months, because that was too much for you guys. And if you guys liked this and you were interested in it, I have some new community challenge things. One of them is almost done with the points, which is me going through some of my old PowerPoint slides that I have from old presentations, and I'm just going to try to give one of these presentations off the, after not reviewing it for however many years since I made it. And the other one is Physics Get Ready With Me, where I'm going to try to do, like, those good old get ready with me, like, when people do, like, makeup videos and they talk? I want to do that, but about, like, physics stuff. But here's the thing, I'm not really good at doing makeup, so it's I just think it'll be kind of funny. It might be entertaining. Sticking my toes out into the ocean. Pretend that's a phrase. Oh my god. Yeah, I forgot what I was... Oh my god, that's such a funny clip. That's such a funny clip. It's a phrase now. I was dipping my toes into the ocean. But yeah, no, but so it's gonna be me, like, trying to do two things at once, and that's, it's gonna be a mess. But I'm excited. I think it'll be a fun mess. It'll be a mess, but it might be fun. Yeah, and we're 4K away from old slides, so once that's raised, that one's nice because I have a few old slides, like, in my pocket, so I don't need to do any prep for that. I can just be like, oh, we raised enough points, let's just do it. Like, it's straightforward. Like, this one needed some prep. But, yeah, if you guys are interested, I can do another physics lecture in the future that's more akin to this one, but maybe with a little more planning because I won't have a midterm right before. So, like, maybe I'll have more time. But, yeah. What's your favorite calculator? It's the calculator I have. It's a TI-34. It's, like, kind of a shitty little... I mean, it was not cheap, but it's not a graphing calculator. It's really kind of simple, but I love it so much. It's so straightforward. Although I've had it for so long that some of the like, oh, I guess I could do it like this. Hold on. Some of the like things have rubbed off on like what they're supposed to be. So I know how to use it, but if I let someone borrow it, they get like confused cuz like the numbers are kind of wearing off. And I'm like I could probably get stickers for them and stuff, but it's pretty good. The TI-36X Pro. Is that a graphing calculator? Is that the graphing one? But it's pretty cute. I have it set to scientific notation, which also kind of messes people up, but it's easier for my brain. But yeah, that's my little calculator. I know. I use Wolfram Alpha a lot though as a calculator. I don't use my little one too much anymore. This one's good because it's not a graphing calculator, you can't program it, that you can take it on most standard tests, which I like too. Okay, it's not a graphing one. Yeah, but they're good, you know? I like my little calculators. But I use Wolfram a lot for like homework or just like general, because Wolfram's pretty good. Pretty powerful. I technically have the like upgraded version of Wolfram through school, but I never use it. So you don't really need it. But that's good. It's all good in the hood. Anything else? I don't know. I'm going to be traveling upcoming in the streams. Are you doing work in the other room? That's all good. No problem. So I'm going to be going back California way on Monday. An HP 55. Oh. But I'm going to California on Monday. So Monday stream might be canceled because I think I'm gonna show up in California later than I normally stream. But it uses reverse Polish notation entry and has an LED display. Oh! That sounds fancy as shit. I kind of want a calculator with an LED display. Am I a little bit jealous right now? Is that the sensation I'm feeling in my body? 1977! That's crazy. That's cool as shit, dude. Whoa! That's crazy. Oh my god. Yeah. So Monday stream, let's just cancel it. I do want to play Liza P, so I might push it to Tuesday, because I'll be on spring break, so I can do whatever I want. But, I'll do... Everything else should be the same. Everything else should be straightforward. So I'll let you guys know. I'll be streaming. I might miss next Friday, but we'll keep in touch. If you're in the Discord, you'll know what's up. You'll see how it goes. It is what it is. But yeah, that's it. If you're watching this on YouTube, I have to address the YouTube audience really quick. If you're watching this on YouTube, hello, welcome to youtube.com. I'm also on YouTube. What do I say to the YouTube people? You can join my Discord. YouTube, in all my YouTube videos, I put the Discord link in the description, but no one ever clicks on it as far as I know. I have no idea. But yeah, so if you're on the YouTube video watching this later, I'm sure all these things will still exist in the Discord. So like, go join my Discord. And yeah, also the ASMR thing was a joke, so I'm sorry. I'm not really being an ASMR person. That was my April Fool's joke following the past year when I said I was gonna be do only pet videos. That was also a joke. So that's my haha hilarioso. And yeah, catch me on Twitch live or leave a comment. I actually love it when people leave YouTube comments because it's cool. I like to know what people are saying. But yeah, that's physics, baby. I don't know, drink water, eat food to sustain your human form, and I'll try to get if I don't put up the solutions to the quiz, just remind me, because I'll forget. I'll just totally forget. Just remind me. Anyway, that's it for me. Yeah, I love you or something. Bye.